Yes, so I'll talk about Atelier algebras and with equivalence for braided fusion categories. So let me give the definition right away. So an Atelier algebra in C. So C, let's assume that C is non-degenerate. Braided fusion category is a commutative separable algebra. So here a commutative means that multiplication does not change when we apply the braiding. And separable means that multiplication viewed as a morphism from A tensor A to A splits, so it has the right index. Now, these properties ensure that the category of A modules is a semisimple category, that it's fusion and but it has rigidity and it's semi-simple. So that's what we do with Atelier algebra. Now, so for example, I should relate this to the previous lecture. Of course, if you take C to be rep G and A, the algebra of functions on C, that's of course a commutative separable algebra. It's in Atelier algebra. So that was the algebra that we used yesterday to do this de-equivalentization. So some of the constructions I'll do today, you would recognize that they're more general than what we did yesterday.
I have a quick question.
Already? Okay.
So for the splitting of the multiplication, I feel like I've seen the answer to this before, but I don't quite remember. Is that a property or extra structure?
That's a property.
Okay, thank you.
Yeah, it does split, so it does not. Yeah. Well, that's what I need at the very least. So, okay. So, what do we do with Atelier algebra? So, we form the category like we did the last time, CA of A modules in C, and this is a fusion category. Furthermore, there is a free module functor. Free module functor from C to the category of A modules that takes an object and assigns the free module to it. Is a tensor functor. And again, yesterday this functor occurred as the de-equivalentization. So de-equivalentization is a special case of this. Now, furthermore, this functor is central. Let's give it a name. Let's call it F8. It is a central functor. So what I mean by that is that it goes, that it factors through the braided tensor functor Z to the center of this category of A module. So this is braided. And in other words, that there is a central structure on each free module. And this central structure is not hard to describe, namely what we want to do. We want to be able to permute this free module with every module in CA. But now, what is this? Now, of course, this CA, where it is, it's a tensor category, and the tensor product is the tensor multiplication over A. So this is Y tensor A tensor X. So this is just Y tensor X. On the other hand, if you do it the other way around, tensor in this order, then it's going to be A tensor X tensor AY, and this is X tensor Y. Now, there is a braiding in C that maps one into another, right? So this is C, Y, X, and this gives the central structure, right? So these two objects can be permuted. All right. Now, it turns out that that's actually something that characterizes Atelier algebras. Kind of using these boards. Okay. All right. So conversely, you can recover Atelier algebra from every central functor. So given a central functor, and central tensor functor from C, let's say from C to some center of a fusion category and to A, like this. So we view it ultimately as a functor from C to A, but it factors through the center, right? So images of objects have central structure. So then what we can do, we can take its right adjoint. Now the adjoint of a tensor functor is not a tensor functor in general, of course, but it takes algebras to algebras. So in this case, when we apply this adjoint to the unit object of A, the result is an algebra, is an Atelier algebra in C. And let's call it A just like I did before. And in this case, category of models over this algebra is equivalent to the image of C. So it's kind of an opposite construction, right? So we go from an Atelier algebra, we construct a central functor. From a central functor, we construct Atelier algebra. We have this sort of bijection. So Atelier algebras, C. And here we have central functor from C.
Where
yeah.
does the Atelier condition come?
Okay, so Atelier is needed for two things. So first of all, in order to tensor models over an algebra, we need it to be commutative, right? So that's commutative property. Now, but we also want the category of models to be rigid and semi-simple. This is not guaranteed, right? Just take a commutative algebra over vector spaces. If it's arbitrary, then the category of models is not semi-simple, right? But separability is a very strong property, okay? It ensures both rigidity and semi-simplicity of the category of models. Now, I did forget one condition to put here, so I'll include it here. So we assume that A is connected. Connected meaning that the home space in C, that identity is contained with multiplicity 1. And that would ensure that the unit object is simple, okay? Otherwise, what you get is sort of multi-fusion category. It satisfies all the properties, except that unit is no longer simple, okay? So this will be assumed. No, well, A, well, if you view it, so we view A as the unit object of CA, right? And as such, it may or may not be simple. If you impose this, then it is simple. That's what I'm saying. As an object of CA, of course, is very far from being simple, like the algebra of functions. Okay. All right. Now, so let's continue this. So here, so inside, and many of these things we saw yesterday, but there the context was slightly different, right? We worked with special type of Atelier algebras that come from Tannakian categories. So what I'm doing today doesn't require Tannakian categories, subcategories. So now inside the category of CA, there is a braided subcategory CA0 of so-called local models. So let me define what these are. So this category CA0, it consists of all models over A satisfying the following condition. So let's say, suppose let's denote module action, let's say by row. Okay, so now then this row is invariant with respect to the squared braid. So this, if we apply, if we square braid A and then with itself, then the module multiplication does not change. Okay, so you have seen this condition. It's necessary to ensure that you can braid models. Okay, so CA here is just a fusion category, and this is a braided subcategory. All right. Now, so how these things are related, and that's something that is going to be important for the rest. You see, so here C is embedded into the center, and this is also embedded into the center. So the center of the category of A modules is equivalent to C tensor the category of the reverse of the category of local modules. So again, how does one prove this result? We already discussed that C is embedded into the center. Where is it? Yeah, here. Okay. And this is also embedded by virtue of it to be braided. So in fact, this category is embedded twice with its normal braiding and with its reversed, right? So this is, of course, a special case of this. Case would correspond to situation when there is trivial algebra. And then we have this result that I mentioned earlier in this course, that this C is equivalent to C tensor C reversed, right? So that's a counterpart of that. Okay, now I always assume that C is non-degenerate. So in this case, you can actually compute dimensions of the categories that we obtain. So Frobenius-Perron dimension of CA is the dimension of the original category divided by the dimension of A, and Frobenius-Perron dimension of the category of local modules is the dimension of C divided by the square of Frobenius-Perron dimension of A. Again, if you want to think about, if you want an example that would help you to think about in the most elementary terms, then remember how we went about quadratic forms. So if you have, quadratic form Q on a group A and E inside A such that Q restricts trivially on it, that what you can define a new group with a quadratic form. And you can, of course, compute the order of this group, right? And it would satisfy the same form or the dimension, the order of the group.
No.
Oh, see, here is a square. I'm sorry. Square, yes. So, right. So it will be the order of the group divided by the square of the order of the isotropic subgroup.
I think there might be a typo. I'm not sure. It says you said Q restricted to A is trivial, but A is the whole.
Q not to A, to E. I'm sorry. I'm going too fast. Yes, of course. So
Thank you.
again, this would be, so this E would be an analog of an Atelier algebra, right? In this case, Atelier algebras come from isotropic subgroups. So again, the moral is that what we are doing is sort of like taking a quotient, subquotient of this.
Dmitri, and you say that you are always assuming non-degenerate. Do you use the non-degenerate in the last statement, in the center thing, or?
Well, yes, I mean, you need, because if C were degenerate, it wouldn't be a direct factor of the center, which is not degenerate. Right?
But do you use it in any other place or just there for now?
I'd like to assume it throughout, otherwise I'll get confused about what is, well, and to be honest with you, like later you'll see categories that are degenerate, but they will be slightly degenerate, okay? So all in due time. Okay, so, right, okay, so now, okay, this all works well, provided that we can find a non-trivial Atelier subalgebra. But if we cannot do this, then we get a rather special category that deserves a special name. So we say that C is completely anisotropic if it has no Atelier algebras other than the trivial algebra 1, which is always an Atelier algebra, but a very boring one. Okay, now how can we obtain such such a category? Well, we do something similar to what we did when we extracted the core of a braided fusion category. Namely, we have this theorem that if A inside C is a maximal connected Atelier algebra, then the category of local modules is completely anisotropic. And furthermore, it doesn't depend on the choice of A. So it is an invariant. If you pick another maximal isotropic, a maximal algebra, you'll get the same result. Also, CA0 like this equivalent CB0 if A, B are maximal at R. So this is significant, right? We extracted an invariant of a non-degenerate category, namely a completely anisotropic category. So we will see that it's invariant of a certain equivalence class called the width class of C. But before doing this, well, I should ask for questions, of course, if there are any. And if no, then let's consider another extreme. So another extreme is when C contains Atelier algebra A such that the category of local modules is trivial. So such A should be called and is called a Lagrangian subalgebra. So we call such a Lagrangian algebra. Well, what happens in this case? Well, this formula tells you everything, right? If the category of local modules is trivial, then it disappears from this, and your C is the center, right? So then C is the center of the category of local modules. So this, in fact, is a characterization of centers. So we have this statement. So I stated as a bijection between two classes of things, namely, let's see, I stated like this. On one hand side, I'll have just fusion categories. On the other side, I will have braided fusion categories, non-degenerate fusion categories containing a Lagrangian subalgebra. So there is a passage in both directions. Namely, in this direction, you start with A, and you produce the center of A, and the center of A, where was it here? Here. So the center of A does contain a canonical subalgebra, which is obtained by induction, right, of this Lagrangian algebra. Well, there is a way in the opposite direction, which is easier. So here, let's give Lagrangian algebra a name. So here you go from C to CA. Start with a braided category, produce a fusion category. So what I was trying to explain for the last 20 minutes, that these two constructions are inverses of each other. Okay, but so there is a name for such things. They are called quantum Manin pairs. So there is a notion of a Manin pair used in the study of quasi-algebras. And so this is kind of categorical version. But what it really means is that the study of fusion categories can be actually, is a part of the theory of braided fusion categories, right? So everything to know about A will be contained in this data, yes? Which is, might sound a bit surprising because on the surface, a braided fusion category is a fusion category with additional structure, right? So kind of theory should be more complicated. Well, exact opposite is true. Okay, so the theory of braided categories is easier and in fact includes, the theory of all fusion categories. Okay, so I mean, again, one can continue to talk about the sort of like geometric approach to this. I would not do this now. Instead, I'll talk about so the main topic I wanted to address today is the width equivalence. So we are going to introduce a certain equivalence relation on the set of non-degenerate braided tensor categories. The width equivalence. Okay, so definition. So two non-degenerate braided fusion categories C1, C2 are width equivalent. We can say categorically width equivalent if we have a braided equivalence of this form. C1 tensor center of something is equivalent to C2 tensor of something. Okay, so this sort of relation, they differ, but their difference can be captured by tensoring them with the centers, right? Fusion categories A1 and A2. Again, this story does exist in the non-semi-simple world, but to be honest, nobody really knows, if the group, if there are kind of with classes that are truly non-semi-simple. So all known ones are semi-simple. So this is pretty much the general state of affairs. Now, let W be the set of width equivalence classes. We observe right away that this set is in fact a monoid, right? Because if you have two categories C1 and C2 with equivalent, and then I don't know D1 and D2 with equivalent, you just tensor these things, right? So this is a monoid with respect to tensor product. In fact, it's a group. And so the unit is of course the width class, well, of any center. And furthermore, there are inverses, and this is thanks to this, because you can always tensor C with its reversed. That's the thing I had earlier today on the board, right? And this is the center of C. So which means in terms of width equivalence that for every C there is a reverse. So there is the inverse, yes? So let's use this notation. So we will denote like this C, the width class C, and then of course the inverse of the width class is the width class of the reverse. All right. Now we can now well, it's worth of course mentioning which categories are in the trivial class. So here I think it would be appropriate to denote like the width class like this, the trivial width class like this, the width class of the trivial category. And then one shows that C belongs to the trivial class if and only if C is the center of some fusion category. All right, so here is what's going on. So you can think of this, of this width group that we construct as a quotient of the monoid of all non-degenerate braided categories by Drinfeld centers.
This is maybe a strange question, but just it goes a little bit orthogonal to this, but this out of curiosity, like all the width equivalent categories, do they really form a set? Is this known, or is this like some more
well, they form, well, if you look at their equivalence classes, then they form a countable set. There are only countably many non-degenerate categories. Yes.
Okay, so it really is a set. Okay.
In fact, it's less obvious at this point, but this is a countable group, and in fact, we will be able to say quite a bit of things about its structure. Okay. Now the previous discussion actually quite related to what we were doing. So because of of this equivalence that we had seen. So we saw that the center of so given an Atelier algebra, the center of CA is C tensor C local models reversed. But in the Witt language, this means, of course, that the Witt class of C does not change when you replace C by the category of local models. This also means that inside every Witt class, there is a unique, completely anisotropic representative. Unique, completely anisotropic representative. This would be true for any algebra, for any Atelier algebra A. If you take it maximal Atelier, then you will get a completely anisotropic. And I just discussed that they're all equivalent, right? So this thing is well defined. Now, as everything that I'm talking about, there is a classical, of course, path to this story. So there is a classical thing called the Witt group of non-degenerate quadratic forms. And I'm not going to recall its definition because it's defined precisely in the same way, that I described here. So instead, I'll say that the Witt group W, so we'll call it the categorical Witt group. So it contains a pointed subgroup. Well, I call it like this W pointed. Inside V, consisting of Witt classes of pointed braided fusion categories, or as it is called in the literature, the Witt group of quadratic forms. Okay, so this is extremely well known since Witt, of course, was responsible for this. So this decomposes into a direct sum over primes. Right, since every abelian group is the direct product of its COP subgroups, and here each of these groups is known. So this is so each of these summands is known. W pointed P. Now it is most non-trivial when IP is equal to 2. It's Z8 cross Z2 when P is equal to 2. It's Z4 if P is congruent to 1 mod 4, and it's Z2. I think it's 3. I think. Let me double check. No, it's Z2 cross Z2 in this case, of course. And Z4 if P is congruent to 3 modulo 4. And you can just explicitly write down elements of these groups, all these non-degenerate quadratic forms on abelian groups of small order. Okay, so now, and of course, now the question arises, what else is there? Well, it turns out that there are many non-degenerate braided categories that are not centers of anything. And a source of them is the following. So we start with G simple Lie algebra and L non-negative integer. Then what we can do, we can form an affine Lie algebra G hat and consider the category which I'll denote like this C GL. It is the category of integrable highest weight, highest weight modules over affine G algebra or at level L. I mean, the same category can be obtained from vertex iteration algebra, right? So it's rational vertex iteration algebra where, I mean, some people should be able to say it better than I, where this at level A, there is this highest representation, something like that. Yes? Okay, there is yet another source of it to define it as a semi-simplification of the category of representations of a quantum group it's an appropriate root of unity. Again, some people will give lectures on that, so I'm not going to go into this. But now, two things that I'd like to convey is that these things are very non-trivial and almost never are centers. Okay, so they give rise to non-trivial elements of the width group. So non-trivial elements of the categorical width group. And one can actually at this point formulate a conjecture, which is again can be known to people in different areas, under different names. Namely, we can ask this question whether is it true that the categorical width group generated by the width classes of these categories. Now, they are not linearly independent in general. There are interesting relations between them, linear relations between them, and come from conformal inclusions. Okay, and sometimes they factor into a product, but for what we know, the known width classes are obtained from them. So in conformal field theory, people ask if rational conformal field theories come from WZW models and orbifolds. That's exactly what I'm saying here, right? So orbifolds correspond to centers, WZW models correspond to this. So this is kind of a formalization of this, which in my opinion is already, good reason to study such things. But but let's not deviate from the purpose. We introduced a certain group. Well, we'd like to know something about this group. So we'd like to discuss the structure of W. So in particular, at this point, let's see. It's not, it's clear already, of course, that it's an infinite group, right? But one can ask questions about like, what's the torsion of this group, right? Does it contain like Q as a subgroup or things like this? So we can say actually quite a few things about the structure of this group. And in order to address this, however, I will need to introduce some close relative of the width group called the super width group. So we'll define our definition. I just a definition. So something like this I said before, we say that C is slightly degenerate or super degenerate. Sometimes people use the word supermodular, but I'm not considering the Riemann structure. If the symmetric center is the category of supervector spaces. Now, I try to emphasize the significance of this, because you see, like, if the symmetric center is always symmetric. If there is a Tannakian part, you can mod out by this, right? So the smallest thing you get, the core, will be either degenerate, non-degenerate, or slightly degenerate. So that's another possibility. So in a sense, slightly degenerate categories are easier than degenerate ones, because you can turn non-degenerate into degenerate just by taking the product with the SVEC, right? It's not so obvious how to go other way around, how to go from slightly degenerate to degenerate. Okay, so and it has like better structured theory. So we will also say that if a fusion category over SVEC, fusion category A, along with embedding of the supervector spaces inside the center of A. Okay, so in other words, A contains a central copy of supervector spaces inside. So we can now, try to forget for time being about non-degenerate categories and play all these games that we had with slightly degenerate categories. So in particular, one can introduce something we can call like the supercenter of such A. Namely, well, we'd like the supercenter be to be of the appropriate nature, so also have a super part. So what we can do now, we can take the center of A and consider the centralizer of supervector spaces that sits inside. So what the result will be a subcategory of index 2 inside the center. So I'll denote it like this. ZA S vec. So such a category will have Z2 grading, and that's the trivial component of this 2 grading. The supercenter. Again, it's a canonical thing, right? Because it only depends on this embedding. So any questions so far? So like all of a sudden, I decided that, we will need like a super version of this theory. That's things that people usually do, but here there is, of course, a good reason for that. Namely, we can define the superwidth group. The superwidth group, I call it like this, SW, of slightly degenerate categories. Again, the same definitions will be given, the same formulas will be written, the only difference is that we work over super vector spaces all the time. Now, and the advantage of this super thing is that there is a better structural theory. So there is a sort of like Wedderburn decomposition into a direct product of simple. So namely, we have the structural result. So let's see, be a completely anisotropic, slightly degenerate, super degenerate category. Then there is a decomposition of C into a direct product. Now, direct products here will be taking over the category of supervector spaces. So it has a pointed part, and then some number of categories S1, etc. Sorry, C1, etc., Cn, where these are simple, completely anisotropic. And this is pointed, completely anisotropic. See, here the word simple means that there are no proper subcategories other than SVEC, which is a part of the structure. So this resembles in some sense like this result in Lie algebraic theory, where we separate the solvable and semi-simple part from it, right? And the semi-simple part is a direct sum of simples. Okay, but this is great. I mean, it suggests that at least the superwidth group would have a nice decomposition into the product of cyclic groups, and this is what is happening. So one thing that one has to answer is the following. So one has to understand, relations between this simple, completely anisotropic categories, right? If there are any. Well, it turns out that there are only some basic relations. So namely, if you have something like this, you have a product of simple categories to be the supercenter of something, then how is this possible? Well, it is possible, of course, if you combine categories and their inverses, right? If everything comes with an inverse. So this is happening if and only if there is a permutation sigma in the symmetric group Sn such that sigma I is the reverse of Ci. So in other words, things here should cancel, right? For every category there should be an inverse. Okay. Now, well, this leaves just one possibility. It can happen that the category is its own inverse, right? And occurs twice. So again, the way to read it is that there are very few relations other than obvious x times x minus 1 is identity. The only possibility is that x squared is identity. All right. So now we can state the main result. Well, one structural result. So it is possible to completely describe the superwidth group as an abstract group. The superwidth group is isomorphic to, well, first of all, of course, the width groups are abelian, right? The tensor product of non-degenerate categories does not change when you replace the factors. So this is a direct sum of three things. It's a pointed part, SW pointed, which comes from this. It's kind of super version of this, can be completely described. So plus W2 SW2 plus SW infinity. Where this thing, so this is a pre-abelian group of countable rank. And this is elementary abelian two groups, abelian two group, also of countable rank. So this does not quite answer the question, right? So, the question was concrete, whether we have a specific set of generators, right? This describes this as an abstract group.
I'm sorry, what is an elementary abelian two group?
It's a group where every element has order 2.
Oh,
So
okay,
it's a
thank you.
direct product of copies of the two, countable product of copies.
Thank you.
Okay, now, but again, it's an interesting thing in itself. And also I should mention that one can replace SVEC by any symmetric category and do studies there. But my purpose was to study the original Witt group. So there is a homomorphism. The Witt homomorphism from the Witt group to its super counterpart.
Mhm.
And that's a very simple thing. Namely, we will send the Witt class of C into the Witt class of C tensor SVEC, right? So this is, I had it on the board somewhere. So this is how we can turn non-degenerate category into a slightly degenerate, right? Multiply by this, and then take the Witt class. Okay. It is important and a very non-trivial result that this is subjective. That's a recent result of Johnson, Freid, and Reuter. And what is easier than that is the kernel of this. Let's give it a name. Let's call it capital S. So S is subjective. The kernel of S is easy to compute. So this is the cyclic group of order 16. And somehow this fact is very significant in physics. There is a so-called 16-fold way, or Kitaev's 16-fold way. Anyways, and it is generated by the Witt class of an Ising category. I should say an Ising, because there are 8 different Isings, but they all generate non-equivalent Isings. They all different in the Witt group, but they generate the same subgroup of order 16. And so we have an exact sequence, so 0, Z16, WSW 0. And we know very well the structure of this, right? I just explained what that is. So this is a non-split extension. And in particular, it has several things. So first of all, the Witt group has no odd torsion, right? There are no elements of odd order bigger than 1. W has no odd torsion. There is a 2 torsion, of course, and the largest order of an element, the largest finite order, an element in the Witt group is 32. So the largest finite order is 32. So these things are going to be the square roots of Isings. Right, something that when you take a square has order 16. So these are the classes of categories S, C, that's S O to n plus 1 at level 2n plus 1. So these are the special n bigger or equal than 1. So these are the special things that appear over here that are responsible for this mysterious part of the Witt group. All right. So this is what is known about the Witt group at this point. Okay, so we know it as an abstract group. We know some relations between these elements, but we don't really know or have an idea really how to approach this conjecture, to show that they generate the whole Witt group.
Then you have labeled this question is promoted to a conjecture.
But I guess you can do this with any question, right? It's just like conjecture is a question with an attitude, right? That I don't really have, any good, evidence or counter evidence.
Question. So, special orthogonal category. When you say the level is 2n plus 1, this is a shifted level where we shift by the dual constant number. Or I think when the level is 1.
Yeah, it's not the same. It's not the same as the order of the root of unity. It is shifted by that. Yeah, I think that what you're saying is exactly right. Yes.
Yeah, it's a dual cost numbers to where on level one, you have an extension which is a whole bunch of variants.
That's right. It is shifted there.
Can I ask, is there a particular, like, intuit, like 16 is a weird number, like where does it,
Second.
16, like where does it come from or something?
Okay, this I can explain. All right. It comes from the following fact. So there is a notion of which I have not used like in this lectures, but there is a notion of a central charge. Central charge of C. Well, I think. Do you know what that is? No. Are you familiar with this? I can define the central charge. So the central charge is the following thing. So what you do, you take a Gaussian sum, which is a summation over all simple objects, like theta x, dimension x squared. Well, it turns out that this sum is proportional to the dimension of C. The coefficient of proportionality is some root of unity. Again, this coincides with the notion of a Gaussian sum of a Gaussian sum that we associate to a quadratic form. Okay, and so it turns out that for the central charge of an Ising category is a 16th root of unity. Okay, so in other words, like these things that you see here, they can be distinguished not just by groups, but just by scalars. There is a canonical way assigned like certain root of unity. And in case of the Ising, it's a 16th root. Okay, so this embedding here is like associated just with taking central charge. That's what I can do.
Yeah,
it does sound mysterious, but maybe not so much so after you see that there is already the A.
Okay, thanks.
Next, please.
At least, right. So okay, so now this would make sense in the category which is ribbon, but the Ising category certainly is. So you can take about this.
So when defining width equivalence, you mentioned it can be defined in the non-semisimple setting as well, but
Nothing really prevents you from doing like the same things, right? You just take appropriate class of algebras, right? So that the categories they produce are rigid. There is like appropriate notion, and it's also called separable, I think, in this case. Now, but you can do all this. You can define such things. The thing is that I don't know anything, in this kind of big non-semi-simple with group that wouldn't be width equivalent to semi-simple things. For example, let's take the category of representations of quantum group at root of unity, right? Well, it has a very large subalgebra, namely Borel subalgebra. If you take the local modules, you'll get Cartan, which is pointed semi-simple, right? So you don't get anything new there, for instance. And all other examples of this sort are like that. So that's why, at present, there is not much loss, of reducing this to semi-simple.
I mean, is there any, from the way you've presented it, the answer is probably no, but is there any hope of being able to study the WIT classes in any more detail, right? So now you've basically got a good handle of the WIT group, and so you know what the WIT classes are. But can you now, inside the WIT, I mean, you've got like your preferred totally anisotropic representative of each class, and could you from that try and get to like less trivial classes? Or...
Well, I mean, I don't know how to produce new things, like, well, one can actually look at this and, study algebras inside, which is a hard problem in itself, and produce this completely anisotropic representatives. What one can do after that is to try to study relations between them. Maybe like, this, completely anisotropic things are linearly dependent, and sometimes they are. But it's not quite an answer to your question. So you ask if we can produce something totally new. I mean, all things I've seen so far, they're, trying to produce exotic things. They work like this. People produce a fusion category and take its center, which is complicated, exotic in a way, but not in the width group. In the width group, it's trivial. So how to produce kind of exotic non-centers?
If there are no other questions, thanks again, Dmitri, for your